This question asks you to check your understanding of the shapes and meanings of the outputs from the make_sparse_coded_signal function. I'll guide you to determine which statements correctly describe the generated variables x, dictionary, code, and error. This statement claims that the variable x is a 10 by 10 matrix and represents the generated signal. I'll help you verify if this is correct. Let's see if this matches what we expect. This statement asserts that the dictionary variable is a 10 by 5 matrix representing a dictionary used to generate the signal. I will go through the function's parameters and their effect on the shapes of the output matrices to verify. This statement proposes that the code matrix is 5 by 10 and represents the sparse code used to generate the signal. I'll verify this statement, paying close attention to the number of rows, components, and columns, samples. This line refers to the core function we're working with, which creates a simulated sparse signal. I find it helpful to think of this as a function that builds a signal from a set of building blocks, the dictionary, and a recipe, the code, of how much of each block to use. This parameter sets how many signals the function will generate. In this case, it's set to 10, so we expect multiple signals as output. This parameter defines the number of basic signal components. In our example, there are 5 fundamental building blocks. Think of it as having 5 different musical notes. This parameter controls the sparsity of the code, indicating that only 3 components will be used to create each signal. We'll use this value to better understand the structure of our code matrix. This sets the length, or dimensionality, of each signal. Here, each signal has 10 features, like 10 different aspects of a data point. This is the matrix containing our 5 basic signal components. Each component is represented by 10 features, which means that the size will be 10 rows x 5 columns. This matrix indicates how much of each component is used to create each signal. Since there are 5 components and 10 signals, the matrix size will be 5 rows x 10 columns. Remember, only 3 components, features, will be used per signal due to the sparsity setting. This variable is a vector. Each element will show how accurately the generated signal was recreated from the components using the sparse code. We expect 10 values, 1 for each generated signal. I'm using the Sklearn libraries make_sparse_coded_signal function. This function creates a simulated sparse signal, which is a signal represented using a minimal set of components. I'm generating 10 samples or instances of my sparse signal. Think of each sample as a different observation of the signal. My sparse signal is represented by a combination of 5 basis vectors or components. These are the fundamental building blocks of my signal. Each sample of my signal has 10 features or attributes. These are the dimensions of my signal space. To make the signal sparse, I'm only allowing 3 non-zero coefficients in the code matrix. This means that each signal sample is a linear combination of only a few of the components, resulting in a sparse representation. I'm setting the random seed to 0 to ensure that I obtain the same results every time I run this code. It makes the experiment reproducible. This is the generated sparse coded signal itself. It's a 10 by 10 matrix because I specified 10 samples and 10 features. This is a 10 by 5 matrix. It represents the dictionary of atoms used to generate my signals. Each column is a basis vector or a component, and there are 5 such components. This is a 5 by 10 sparse matrix. It shows how much of each component is used in each sample. Since I only used 3 non-zero coefficients, most of this matrix will be zeros. This represents the reconstruction error, which is a vector of length 10, showing the error for each sample. It's how much the reconstructed signal differs from the original signal. I'm generating a sparse signal, which means it's represented using only a few non-zero values. Think of it like a really efficient way to store information. It's like a secret code. It's super cool. This is the function from the Sklearn library that I'll use to create my sparse signal. It's like a magic wand for sparse signal generation. I'll generate 10 different sparse signals. Each signal is like a unique message. I'll use 5 basic building blocks to create my signals. Think of them as the basic ingredients to make the signals. Each of my signals will have 10 characteristics or features. Each feature could be something like the intensity of a color in an image. Each signal will use only 3 of the 5 building blocks to create them, ensuring sparsity. It's like using only 3 ingredients from the 5 available to make a dish, keeping things simple. This variable holds the actual sparse signals I created. It's the main result, the final message. The shape means I have 10 signals, rows, each with 10 features, columns. This is the collection of my 5 basic building blocks. I call them dictionary atoms, each with 10 characteristics. They are like the fundamental elements I use to construct my signals. The shape indicates that there are 10 features, rows, and 5 building blocks, columns. This shows how I combined my building blocks to make each signal. Because it's sparse, only a few values are non-zero, indicating which blocks I used for each signal. This means there are 5 building blocks, rows, and 10 signals, columns. This measures how well I could reconstruct the original signal from the building blocks and the code. A smaller error means a better reconstruction. The error is a one-dimensional array of length 10, showing the reconstruction error for each of the 10 signals. I'm generating a sparse signal, which means it's represented with a small number of non-zero elements. Think of it like a really efficient way to store information. This is the function from the Sklearn library that I use to create my sparse signal representation. It's like a toolbox function providing the tools to create the representation efficiently. These settings control the size and properties of the signal I generate. Let's break it down. _n_samples sets the number of signals, 10. _n_components sets the number of dictionary atoms, 5, which are the building blocks of my signals. _n_features is the dimension of each signal, 10. _n_non_zero_cofs dictates how sparse the signal is. 3 non-zero elements in each signal representation. And _random_state ensures I get the same results each time for reproducibility. This is the actual sparse signal that the function generates. The shape, 10, 10, means that I have 10 signals, each with 10 features. It's the output of the process, the signal itself. This matrix contains the atoms, the basic components used to create the signals. The shape, 10, 5, tells me I have 5 atoms, each described by 10 features. It's like the recipe book that defines how different atoms combine to form the signals. This matrix shows how the dictionary atoms are combined to create each signal. It shows the weight of each atom used in each signal. The shape, 5, 10, indicates that I have 10 signals, and each uses a combination of 5 atoms. This measures how well I can reconstruct the original signal from the sparse representation. A lower error is better, indicating a more accurate representation. The function, simply put, is a tool for creating the sparse representation. It takes certain parameters as input, and it returns the sparse signal itself along with the dictionary matrix and code matrix. This is a matrix storing the actual sparse signal. Each row represents a signal with 10 features. The function gives me 4 things: the signal itself, the dictionary matrix, the sparse code matrix, and the error in the reconstruction. We're generating a signal that's represented sparsely, meaning it uses only a few non-zero values to encode information. Think of it like a super efficient way to store data. This is the workhorse function. It's from the Sklearn library and creates this sparse representation for us. Sklearn is short for Sklearn, a popular Python library for machine learning. These are the settings we use to customize our sparse signal. _n_samples tells the function how many signals to make. _n_components is how many basic building blocks make up those signals. _n_features is the signal's length. And _n_non_zero_cofs tells us how many non-zero components each signal will have at most. Let's break this down. I want 10 signals. Each signal will use 5 basic building blocks. The length of each signal is 10. And at most, only 3 building blocks will be used for each signal. These are the results our function spits out. X is our sparse signal. Dictionary contains the building blocks. Code shows how the building blocks are combined to make the signals. Error shows how well the signals were reconstructed. This is the core question. I need to match the shapes and interpretations of the output variables, x dictionary code error to the given options, A, B, C, D, to find the correct answers. This refers to the steps involved in determining the correct answers, which are detailed in the explanation sections. This is the topic, WERE, generating a signal using a sparse coding technique. Think of it as expressing a complex signal using a few basic building blocks. This is the specific function from the Sklearn library that I use to do this. It's like a pre-built tool for the job. I'm creating 10 different signals. Think of each signal as a different song. I'll use 5 basic components or building blocks to create each of the 10 signals. Imagine these are 5 basic musical notes or instruments. Each signal will have 10 features. Think of these features as the measurements made on each song or the characteristics that define each song, such as loudness, pitch, tone, and so on. For each song, I'll use only 3 of the 5 basic components to create the song. This ensures the signal is sparse, meaning that only a few of the basic building blocks are used in each song. I set the random state to 0 to ensure the results are reproducible. Every time I run this code, I'll get the exact same signals because I'm fixing the randomness seed. This is the set of 5 basic components I use, the 5 basic musical instruments. It's a matrix, a table of numbers, where each column represents one of the 5 components. This tells me how much of each component goes into each of the 10 signals. It's also a matrix. Each column represents a signal, indicating the contribution of the components to each signal. This measures how well the generated signals match the perfect ones. It's a way to check the accuracy of my sparse coding method. Statement A claims that X has a shape of 10 rows and 10 columns. That's correct. It's a matrix representing my 10 generated signals with 10 features each. Statement B says the dictionary is a matrix of 10 rows and 5 columns. That is also correct. It contains my 5 basic components, each described by 10 features. Statement C is incorrect. The shape of the code matrix should be 5 rows, number of components, by 10 columns, number of signals, not the other way around. Statement D is also incorrect. The error is not a single number. It's an array containing errors for each of the 10 signals.